Okay, this is section 7.2, integration by parts, the first day of the section. This is going to be looking at trying to integrate integrals where we can't do a basic U substitution. A lot of times this is going to kind of be basically when you have the product of two functions and you can't just do an integration by substitution. For example, down here you'll see we have x e to the 3x dx. If I was going to try to do a normal u substitution on this, I might make u 3x, but then my du would be 3 dx, and I have this extra x, which causes a problem. So can't really integrate this using some basic integration technique. So what we're going to do is we're going to do something called integration by parts, which if you go back to the product rule for derivatives, the product rule for derivatives says if I have a product of, let's say, u times v, and I want to find that derivative. Well, in one case, we leave u alone, and we take the derivative of v with respect to x. Then I would leave the other part of the product alone, which would be v, and take the derivative of u with respect to x. And then we do the sum of those. Okay. Now, if I then basically take all the dx's and just get rid of those out of the problem, so if I basically multiply that function by dx, I get this equation. If I then integrate, or excuse me, move some terms around there. So if I take this v du term, for example, and subtract it over to this other side, I have that u dv is equal to the derivative of u times v minus the integral of v du. Well, if I then integrate both sides of that equation, I get to here. I have the integral of the left side. The right side, since this was a derivative and I integrated it, would just be the product minus the integral of v times du. This is the whole integration by parts idea. Now, what I have to do is I have to look at my function I'm trying to integrate, and I have to choose something to be u, and I have to choose something to be dv. And then I have to rewrite my function in this form. And often what I end up with is an integral that I can then do a basic u substitution on and finish it. Now, some guidelines. Okay, these are what kind of the book kind of gives you as guidelines, is try letting dv be the most complicated portion of the integrand that fits a basic integration rule. So you have to pick something for dv that you can integrate, because part of your formula is you're going to have to figure out what v is. So you can't pick something for dv that doesn't integrate. Then it says try letting u be the portion of the integrand whose derivative is a simpler function than u. So something that when you differentiate it becomes simpler. Okay? That's just some real guidelines. They don't necessarily work all the time. Now, this is another thing that I've picked up over the years. It's called the acronym I-late may help. Okay? The I part stands for inverse trig functions. So if you're trying to do something with inverse trig functions, okay, that has one of your two functions that you're trying to deal with. Logarithmic functions, A for algebraic, T for trig, E for exponential. The closer a function is to the top of that acronym, the more likely that it should be u. Again, this does not work in all cases, but more likely you should at least start this way by making the closer one to the top of that acronym, you should make that u. The closer a function is to the bottom of this acronym, the more likely it should be dv. And again, there are exceptions to this. They're just guidelines. In some cases, you'll have to use trial and error. Okay, so in this particular situation, I already talked about how we couldn't do a basic u substitution on this, because if we made u 3x, we have this extra x out here, which causes a problem. Okay, now I'm going to divide this basically into two separate functions. We have an algebraic function, so that's an a. We have an exponential function, that's an e. So if I'm looking at my I-late acronym, okay, the closer a function is to the top of that acronym, the more likely it should be u, and the closer one is to the bottom, the more likely it should be dv. So technically, if you're thinking about exponentials, they're pretty much always going to be what you're going to make dv, okay? At least to try to start. Okay, so I'm going to make ux, and I'm going to make dv e to the 3x. Now, whatever you make dv automatically gets your dx, because you're going to be integrating that. Okay? Du is going to be the derivative of x, which is just dx. V is going to be the integral of dv, so we have to integrate e to the 3x dx. Now remember, when you're integrating that, we don't have a 3 that we would need as part of our dx, so we would have to multiply by 1/3. So the integral of e to the 3x would be 1/3 e to the 3x. You don't need to include the plus c part, okay, at this point. Okay, so now I'm going to rewrite my integral as this. uv minus the integral of v du. So basically down here, if I look at my parts, I'm going to have u times v, so that's going to be 1/3 x e to the 3x minus the integral of v du. So I have the 1/3, I can go ahead and take that on the outside, e to the 3x dx. Now, up here, we had a problem. We had this extra x that allowed us to not use the normal u substitution. But now that we've done integration by parts, we've now gotten rid of that x. It's now not part of my integral. So now I can integrate this, and then I'm going to be able to complete my problem. So I have the 1/3 e to the 3x that I had in the beginning. I have the minus 1/3. Now remember, integral of e to the 3x dx, we just did that a little while ago. We know it's 1/3. So that 1/3 times the 1/3 we already have is going to be minus 1/9 e to the 3x. And at this point then, we have our plus c. Now you may see this done with the final answer. We have an e to the 3x that obviously both these terms have in common. I'm also going to factor out a 1/9 out of my fraction. So I have 1/9 e to the 3x. And then if I divide 1/3 by 1/9, that's going to be 3x, because I have the x left over, minus 1 from this term, plus c. And now I've been able to integrate my expression. Okay, let's try that again. Here I have an x squared. That's an algebraic function. I have a natural log of x. That's a logarithmic function. Again, I can't do a normal integration by or u substitution on a problem like this, because if I try to make this u, that's not going to work. If I try to just make ux, that's not going to work. If I try to make ux squared, no possible u substitution is going to work in this case. Now, using my acronym, logarithm function is going to be more likely to be u, because again, in I late, L comes before A. So I'm going to make u the natural log of x. I'm going to make dv x squared dx. Okay? If I tried it the other way, by the way, I don't have a basic integral for natural log of x. So really, in this case, I pretty much have to choose this, because this is the only one that I can differentiate and make it simpler, and then this is the only one of the two functions I can actually integrate. In this section, or in this chapter, we're actually going to learn how to integrate natural log of x using integration by parts. Okay, my du is 1/x dx. My v is going to be the integral of x squared, which is x cubed over 3. Okay, so now I'm ready to do u times v, x cubed over 3, times the natural log of x, minus the integral of v du. So I can go ahead and take the 1/3 out, then I have x cubed, and I have the natural log of x dx. Oops, I take that back. I wrote that wrong. I did uv, I didn't do v du. So actually that natural log of x is not there, so let's get rid of that. Sorry. So instead it's going to be minus the integral of v du, which one of those x's is going to cancel with one of those x's. I can take out a 1/3, and now I just have the integral of x squared dx. And now I have something that I can integrate using a basic technique. So I have x cubed over 3 times the natural log of x, minus x cubed over 9. When I integrate this, because that's going to be x cubed over 3, plus c. I can factor out an x cubed over 9 out of those first two terms. And I have 3 natural log of x minus 1 plus c. Slide that over so you can see that. Okay, let's try another one. Okay, for this particular example, we have 3x, which is algebraic, and we have sine x, which is trig. So in my acronym, A would be u, so 3x, and dv would be sine x dx. Okay, my du would be 3 dx. My v would be the integral of sine, which the integral of sine is cosine, and also don't forget it's actually going to be negative cosine. I believe I've written that. Yes, because if I take the root of cosine, it would be negative sine, so the integral of sine will be negative cosine x. And we're good. Okay, now we try that. I got u times v, so that's negative 3x cosine x, minus the integral of v du. Now v du has a negative, so I can take that out and make that a plus. I can take the 3 out, and then I have cosine x dx. Well, now I'm good. I know the integral of cosine x is sine x, so we have negative 3x cosine x plus 3 sine x plus c. I could factor a 3 out of there if I wanted to. Okay, next one. We have 2x over e to the 4x. Basic techniques do not work on this one. Now, the one thing before I decide to do integration by parts is, remember, integration by parts, I need to rewrite this as a product. So I'm going to bring that e up and make that e to the negative 4x dx before I do integration by parts. Okay, we have an algebraic and we have an exponential. So I'm going to make u the algebraic function, which makes du 2dx. I'm going to make dv the e to the negative 4x dx term. Integrating that would be negative 1/4 e to the negative 4x. Okay, u times v, so we have negative 1/2 e to the negative 4x minus the integral of v du. Now v du already has a negative, so I'm going to go ahead and take that out and make that a plus. The 2 times 1/4 is going to be a half, and then I have e to the negative 4x dx. Okay, now this term doesn't have the extra x on the outside, so now I can integrate that again. I got negative 1/2 e to the negative 4x. This is going to become another negative 1/4 times that 1/2 is going to be negative 1/8 e to the negative 4x plus c. And then I can factor out an e to the negative 4x and a 1/8. If I do that, this is going to become negative, let's take out the negative too, make this all positive on the inside. So if I take out a negative there, then the 1/2 is going to become 4 and x. And actually that term right there, I think I left out, when I did my u times v, yep, I left out the x. So there's going to be an x there, which means there's an x there. So that's how I got that 4x right there when I took out the negative 1/8 and the e to the negative 4x. And then plus 1 plus c. So again, back there when I did u times v, I left off that x right there. So that should be there, and then when I factor out, I have an x left right there. Okay, last example. Now this one is kind of strange because I don't know what the integral is for arctangent, and we only really have, by looking at it, it seems that we just have one function. Okay. When that's the case, you can still try to integrate these by parts. Here's the key thing, though. I still have this function right here, which is a trig function, or excuse me, an inverse trig function. So that's my I part. Now, when all you have is one function, and then you have dx, that's going to be treated like my other function. Now, automatically, that has to be dv. That's the thing that's going to be integrated. So that's going to be my dv, and then my function that I'm trying to integrate is going to be u. And watch how this works. I'm going to make u arctangent x. I'm going to make dv just dx. Okay, now du is going to be the derivative of arctangent, which is one of our basic rules that we have to know. That's 1 over 1 plus x squared dx, or dx over 1 plus x squared. V is just going to be x because it's the integral of dx. Okay, so now I'll do u times v, which is x arctangent x minus the integral of v du, which is going to be x over 1 plus x squared dx. Okay, now you might think, well, all we have is another integral that looks as complicated. This is not as complicated, though. This one I can do a basic u substitution on. For this integral right here, if I make u 1 plus x squared, and I make du 2x dx, well, I have exactly what I need. If I make this a 2, and I put a 1/2 on the outside, which I'm allowed to do, now I have du over u. So we have x arctangent of x minus, we have a 1/2. We have du over u, which we know is natural log, absolute value of u, so 1 plus x squared plus c. And so I can rewrite this as x arctangent x. I could go ahead and do the power rule, make that 1/2 in there, make this the square root of 1 plus x squared. I don't need the absolute value around that. And then plus c. So if it looks like I just have a function with dx and I don't know a basic integral for that function, I try making that function u, I try making dv dx, and then see if it works. In this section, you'll actually do this for natural log so that you'll actually be able to integrate the natural log of x dx. You'll make the natural log of x your u, and then your dx will be your dv, and you'll actually find out what the integral is for the natural log of x. Okay, that is part 1, or day 1 of 7.2, and we're finished with that one.